I'm Kim Jake Tiani. Welcome to Cooler Facts, the show that's full of surprising facts about the world around us, science, nature, and technology. The first surprise is how we're telling you our stories. Get ready for a fun, fast-paced tour of short little video bits. Each one promises something new, from news on the hottest fires to the world's longest bridge, plus comparing our sun to a beach ball. No, really. But first, you've heard of occupational hazards, right? Well, these occupations are hazards.
Work bothering you lately? Time for a reality check. There are some deadly jobs out there, ones that give new meaning to the words occupational hazard. To shipbreakers in Bangladesh, hazards are a way of life. They take apart giant freighters and five-star ocean liners by hand. Vessels the size of apartment blocks, 10 stories high. When a ship comes here to die, first on the scene are gas cutters, operational infantry who attack the steel hull with gas torches, reducing it to multi-ton pieces. Another crew then reduces these chunks into pieces the size of a school bus. Finally, porters step in.
One, two, three.
Human cranes shouldering the full weight of the ship, lugging the plates into trucks to be hauled away. Keeping the operation going means men working 7 days a week in temperatures hovering at 50 degrees Celsius. Uncomfortable? Sure, but not nearly as hot as an erupting volcano. Ask any volcanologist, the brave souls who predict when volcanoes will erupt. It's important work. 1 in 10 people live within range of an active volcano, and they can go off without warning. Volcanologists make predictions based on the pattern of the smoke and movement of magma. To get a front row view, they chopper over the crater. Some don't return from the journey. No surprise, explosions can hurl ash and hot rock at hurricane speeds, kilometers into the air, enough to take out commercial aircraft. In 1982, a 747 flew into a plume of volcanic ash from Indonesia's Mount Galunggung. All 4 engines failed. Luckily, the pilots were able to find their way out and restart them. There have been dozens of similar incidents. Smoke jumpers know a thing or two about taking heat at work. The world's most elite firefighters routinely dive into 400-hectare blazes from rickety aircraft, aiming for spots no bigger than a baseball diamond, surrounded in tall timber, wearing 30 kilos of protective gear. At least the Kevlar suit eliminates the risk of getting stabbed by a tree branch on the way down. Fully suited, they would be impervious to the blows of a baseball bat. Off the coast of Louisiana are oil rigs, dangerous by their own right, but travel 60 meters down into the murky depths of the Gulf of Mexico, and you'll see some real danger. This is the workplace of the hell diver, a specialized angler who hunts sturgeon the size of horses. They graze here on this man-made reef, a 3-acre maze of legs and crossbeams. The hell diver hunts here with a spear gun. But if the fish survives the initial assault, he's going for a ride. Like a bull rider getting bounced against the corral barrier, he holds on for dear life in this underwater rodeo. Even the dive itself is dangerous. Here, Martini's law prevails. That's the rule that says every 15 meters of depth equals the effects of 1 dry martini on the human brain. That's a 4-martini dip. It gets worse. At those depths, oxygen can actually become toxic to the central nervous system, causing blackouts, hysteria, and convulsions. Pretty grim things in your living room. Imagine it at the depths of the Gulf. And here you thought your job was killing you.
I think my job is pretty safe by comparison. When we think of dangerous jobs, we think of firefighters, right? Starting a fire is pretty easy, but putting it out, well, that's a whole different story, especially one that's been burning for thousands of years.
Each time we watch a fire blaze out of control, we are reminded of the basic rules of fire. It likes oxygen, wood, and usually extinguishes underwater. But sometimes fire doesn't play by the rules. Take a deep breath. Before the 2002 Sydney Games, the Olympic flame was taken on its first underwater journey at the Great Barrier Reef and kept on burning. That was because a formula of chemicals, including combustible magnesium powder, produced enough oxygen and nitrogen to burn the flame at 2,000 degrees Celsius. Instead of collapsing under the water pressure, the flare generates enough outward force to keep the water from entering the tube. Sometimes no amount of water can stop a fire. In June 1969, Cleveland, Ohio's Cuyahoga River ignited. Oil slicks and industrial runoff from local factories caught fire on top of the water. 5-story-high flames burned for 30 minutes until firefighters squelched them. For years, Cleveland had a hard time outliving its environmental disaster reputation as the mistake on the lake. But other unexpected places also burned without kindling, like piles of tires. In Hagersville, Ontario, a fire started in a pile of 14 million car tires. In 1990, they burned for 17 days and nearly forced 4,000 people to evacuate. A single tire contains about the equivalent of 7.5 liters of oil. In this fire, that would have been 105 million liters of oil, enough to fill 42 Olympic-sized pools. In order for a car tire to catch fire, it needs to be heated for at least 20 minutes at 400 degrees Celsius. And putting out tire fires is extremely difficult. Water won't work. It just produces a slick, oily sludge. Smothering the burning tires with soil or sand is the best option. The longest burning tire fire blazed for 2.5 years, from August 1998 until December 2000. The fire ended up torching 7 million tires at a dump in Tracy, California. Other fires hang on even longer. The former coal mining town of Centralia, Pennsylvania literally sits on a hot plate. Started by burning trash in a mine 45 years ago, the coal seams are burning 100 meters underground. Constant access to oxygen through caves and rock fissures keep the embers smoldering. Need a cup of tea? The groundwater in that town is over 100 degrees Celsius in places. It's like living over a volcano. No surprise, most of the town finally accepted a government buyout in the 1980s and left. The fires are expected to last another 250 years. But if you think that's a long burner, try this. 300 kilometers north of Sydney, Australia, scientists believe a huge coal seam has been burning for 6,000 years. Known as Burning Mountain, it's the oldest known coal fire in the world. 19th century explorers mistook the sulfurous smoke as a volcano. When the ground you walk on turns out to be like a giant charcoal barbecue, you need to rethink what can burn and where a fire can't go. Maybe this ought to be a new fire prevention rule. Wherever, whenever, always carry a portable fire extinguisher.
Who knew all those fires were burning underneath us? Next up, from fires to the wettest hotel on the planet. See you in a bit. Welcome back to Cooler Facts. How do bridges stay up? Here I am, suspended 40 feet above an urban highway, standing on tons of concrete. But again, I ask you, how do these things stay up?
The world's longest bridge extends 38.4 kilometers across Louisiana's Lake Pontchartrain. The conventional bridge is made of 9,500 steel pilings supporting concrete spans that are collectively longer than Long Island. But the truth is, some shorter bridges pose much bigger engineering challenges. Like spanning across an earthquake zone in water up to 65 meters deep on a seabed of loose sediment. That's why the 2,880-meter Rion and Tyrion Bridges piers are sitting on top of leveled gravel reinforced by steel pipes rather than buried deep into the ground. When the earth shakes, the piers move side to side and absorb the seismic energy. If you're worried about shaking, You might not want to peek through a glass-floored skywalk that sticks 20 meters out and hangs 1,200 meters over the Grand Canyon. Built 14.5 meters into the rock, the horseshoe-shaped walkway contains 455 tons of steel, cantilevered to sustain the weight of 71 fully loaded Boeing 747s and the force of an 8.0 magnitude earthquake within 80 kilometers. Can you imagine a plastic bridge? Well, it already exists. A 2001 California highway bridge is made of carbon fiber composite tubes encased in plastic and a deck of fiberglass panels instead of steel girders and reinforced concrete. The girders are light enough that 4 men can manage what normally requires a construction crane. And without steel, subject to corrosion, the bridge is less susceptible to damage from salt and water. Sometimes it's not just the traffic that moves, some bridges do too. But the Gateshead Millennium Bridge in Newcastle, England moves differently than your standard drawbridge. A bank of 6 hydraulic rams tilts the entire 773-ton steel structure 40 degrees, so large ships can pass under it in just 4 minutes. Maybe the most daring engineering is to imagine a bridge in one of the most hostile environments, across the Bering Strait. This proposed 80-kilometer Arctic super bridge would span more than twice the length of the Lake Pontchartrain Causeway. Construction challenges include working in sub-zero temperatures and sustaining hits from ice flows. A design already exists for ice flow-resistant bridge pylons. They're shaped like the prow of an icebreaker. The biggest obstacle for this bridge is the price tag, an estimated $100 billion US. But the prospect of Russian oil piping across Siberia to the hungry US market might make this project happen. And with new engineering advances and gas prices, we may cross that bridge sooner than you think.
Okay, now I feel a bit better about bridges. But big buildings? Well, that's another matter, especially the one you can fly a jet through.
Architects and builders have been pushing the limits for centuries. Some of the world's most amazing buildings are built out of experimental materials and in the oddest of places. China's Central Television Network's new Beijing headquarters consist of 2 leaning towers that bend 90 degrees at the top to form a continuous tube. The 30-story high hull of this gigantic steel and glass donut is big enough to fly a Learjet through. The office floor space for 10,000 people is second only in size to the world's largest building, the US Pentagon. The Jubilee Church that opened in Rome in 2003 is made of a special concrete that does not discolor. It not only cleans itself, it also cleans the air by eating surrounding smog. It contains titanium dioxide that triggers a chemical reaction that accelerates oxidation, destroying air pollutants. In New Mexico, there are Hobbit-style pods called Earth ships made from old tires and pop bottles. They survive entirely off the electrical and water grids. The home gets water from rain that collects on the roof. Whatever is used for dishes gets siphoned through a filter of gravel and plant roots. Then it's used again in the bathroom. Considering that the average US household drinks, flushes, and washes about 482,000 liters of water a year, enough to fill over 3,000 bathtubs, these Earth ships are seriously self-sustaining. The Great Mosque of Djenné in Mali is the largest mud brick or adobe building in the world, with a base 40 by 40 meters, about half a football field. It's been the site of a mosque since 1240, but the current version dates from 1907. In the world of experimental architecture, Dubai is the promised land. And when the sky's the limit, go for a swim. Take a look at Hydropolis, promised to be the world's first luxury underwater hotel, to be 20 meters under the Red Sea. This $500 million resort will feature lavish suites, a ballroom, a shopping mall, and a missile defense system to ward off terrorists. To date, it's only on the drawing boards, so don't hold your breath. After all, there are already many other extreme buildings to visit.
An underwater hotel? Only in Dubai. Stick around right after the break. With robots on the cutting edge of science, Why model one after a lobster? More cooler facts heading your way. Welcome back to Cooler Facts, where we present science and technology with a little twist and a bit of a surprise. I'm Kim Jake Tiani. Robots are on the cutting edge of science, but today's robots don't look anything like R2-D2.
For decades now, we've been dreaming of walking and talking robots, androids to help vacuum or make dinner. Well, robots have arrived, just not in the shape or places you'd expect. At Harvard University, they have invented a robotic fly the size of a penny. The RoboFly weighs 60 milligrams, the same as a few grains of rice. A tiny motor beats its wings 120 times per second. The force is 5 times more powerful by weight than the muscles of a real fly. In the future, these tiny flyers will conduct surveillance on the battlefield. The U.S. military already has 4,000 reconnaissance robots scouting for roadside bombs and hunting down insurgent hideouts in Afghanistan. That's the same as 1 robot for every 10 human soldiers over there. In New York, robot takes on a new meaning at this parking garage. It works like a giant robotic jukebox. When you drop off your car, laser and radar sensors confirm the passengers are gone. Elevators whisk the cars away and stack them like pop cans several cars deep. To retrieve the car, swipe a card and the system delivers it in less than 2.5 minutes. That's faster than any valet. Plus, no tip required. Inside the human body, this tiny caterpillar-sized robot will soon help surgeons repair human hearts. Once inserted through a tiny keyhole incision, the robot uses its sucker-like feet to crawl over the heart's surface to position pacemaker leads or inject dyes. Mother Nature is a great inspiration for robotics. That's why scientists turned to the amazing lobster. Turns out they have an incredible ability to sense minute odors in the sea and hunt them down. So, engineers built the Robo-Lobster, a 2-kilogram, 60-centimeter long robot underwater bloodhound. Instead of getting dipped in butter, it uses fiber optic antenna to sniff out hidden mines or locate the source of pollutants leaching into the water. Even humans can use a hard outer skin. Consider the U.S. military's plans to muscle up soldiers. Wearing this robotic exoskeleton, a soldier can carry ammunition boxes the weight of bags of concrete without getting tired. A consumer version is in production for Japan's aging population. The 15-kilo battery-powered HAL-5 responds to electrical impulses on the operator's skin and converts them into instructions to the suit. The cyborg has arrived.
Imagine having a pet robot named Spot. Robots should be able to work for us for an entire lifetime, but they can't hold a candle compared to our sun. It's been doing its job for over 5 billion years, and it's only just reached middle age. More cool facts about our sun and the stars around us when we come back. Welcome back. Who's your favorite Hollywood star? Julia Roberts? Harrison Ford? Mine's right up there. And here's something even the tabloids don't know about my favorite star, the sun.
The life of a star is so violent, so enormous, it staggers the imagination. Our sun, the star closest to us, is no exception. Its raw material is so powerful, just a pinhead's worth could kill someone at a distance of 160 meters. Its visible surface is a fierce churning cauldron of billions of furnace-like cells called granules, each one a kilometer in size. Granules explode, spewing their material into the solar atmosphere at 1,600 kilometers per hour. That's like rocketing over 10 football fields in a second. It's an outrageous understatement to say the sun is hot. The surface is 6,000 degrees Celsius, rising to over 15 million degrees at the core. The enormity of its heat output is mind-boggling. 400 trillion watts. That's 40,000 watts of light from every square inch of its surface. the brightness of 700 standard household bulbs emanating from an area the size of a quarter. Pretty breathtaking when you consider the sun's actual size, 1.4 million kilometers in diameter, 330 times larger than Earth. If it were the size of a beach ball, the Earth would be a pea. And that's just one star amid more than 100 billion in the Milky Way. Next to some other stars, the sun is downright puny. Betelgeuse, one of the stars in the Orion Belt, is a staggering 500 million kilometers in diameter. If it were hollow, the Earth would comfortably revolve around the sun inside it. Alpha Centauri, the nearest star visible by the naked eye, is 4.5 light years away. It would take almost 5 years to get there. If our sun were scaled down to the size of a period on a printed page, Alpha Centauri would be about 14 kilometers away. Because it works so hard, the sun will eventually burn out. The sun's been doing its thing for about 5 billion years. It'll probably do it for another 5 billion. At the end of its life, the star that nurtured us for so long will care little for us. The solar wind will become a cyclone that may even evaporate the atmosphere. The sun, as other stars have done, will explode into a supernova, eventually spinning itself into a neutron star. There is a bright side. The heat from the sun dying may be warm enough to melt the water-rich but frozen moons of Jupiter and Saturn. We humans, if we're still around, might relocate there.
And I thought moving from India to Canada was a big move. Well, that's it for this edition of Cooler Facts, the show that presents a different twist on everything from the coldest place on Earth to the animal with the deadliest bite. I'm Kim Jake-Tiani. Catch you next time for more Cooler Facts.
Welcome to Experimental, the science show for airheads, garden designers, and people who hate washing up. Coming up, why the colour of your car might make seagulls do this, and why being eaten by worms might cure asthma. But first, let's find out what some men don't want their girlfriends to catch them doing in their bedroom. That's right, playing the air guitar, the instrument that brings out the twit in every ageing adolescent. But travel north to sunny Finland and you'll find something quite remarkable.
This is my favorite move.
The air guitar has left the bedroom and is strutting its stuff quite openly in the street. And even odder, some of these airheads are girls. But stranger still, head into the hallowed lab of the Helsinki University of Technology in Finland, and you'll find a group of graduate students, Juha, Timu and Aki, who are dedicated not only to bringing the air guitar out of the bedroom, but making it into a real instrument, capable of bending the ears of the older generation the world over.
So this is the prototype. So I have my virtual air guitar by my hands. I use the right hand for making plucks, and the left hand is used for making slides. And by the right hand, I also have a little whammy bar effect. So mix all this together with some air guitar attitude and you have your rock music. You don't have to worry about playing wrong because the musical intelligence of the system takes care that everything fits nicely together.
It's pretty clever, but doesn't having all those wires connected to your gloves kind of stifle your cool? Welcome now to the wireless air guitar. The idea is that a camera tracks the movement of your hands and then works out their position against a virtual guitar in its memory. The closer your hands are together, the higher the notes.
Instead of using magnetic trackers with wiring, we're using computer vision.
OK, so even the artist at the time of writing known as Prince would not have chosen orange gloves. But there is a good reason for this fashion faux pas.
We chose orange because it's a color not usually found in clothes.
But what's really clever is the computer makes sure that what you're playing actually sounds good. Well, goodish. But how easy is it to play?
Check this.
This player has been on the guitar for exactly 20 seconds, and already the women are flocking to him. Other players who strummed away when the boys exhibited their system at the local science museum didn't have quite the same charisma. But that's one of the great things about their guitar. Even if you can't strut your stuff like Bon Jovi, with a click of a button, you can sort of sound a tiny bit like them.
One of the biggest things was that we added a solo mode where you can use the top 3 strings in the guitar to play solo modes. And the playing mode generally boosts your actions to make the sound more vibrant.
OK, that's enough of the beginners. Let's see the expert air guitarist rip. Ultimately, the 3 boys are going to hit the market with a system that can help you play a repertoire of classic guitar hits. Players will be able to strut their stuff just like guitar karaoke, but the computer will correct all the bum notes. Perhaps in the future, they'll even come up with a microphone that will make you sound like a lead singer. But sadly, this virtual rock star sounded so bad, we had to cut her sound out. In a moment, a shitty story about birds.
Bristol University needs 2 professors of zoology now, don't we?
But first, some practical advice to divers. Welcome to the test department's unlikely survival guide, in which we learn how to kill a great white shark. It's easy. You hold onto its tail to stop it swimming forwards. Why does this work? When a shark swims, the water enters its mouth, then passes out again through the gills on either side of the head. It's the gills that suck the oxygen out of the water, allowing the shark to breathe. By stopping the shark swimming forwards, you'll stop the flow of water over the gills and the shark will eventually drown. However, do remember that some scientific facts are more practical than others. Coming up, the latest in water features for your garden, brought to you by the test department. But first, we're off to the west of England to look at why birds are responsible for that other weekend task, cleaning the car. It's happened to us all. You've spent all Sunday afternoon cleaning your pride and joy when from out of the blue... Yes, quite. Or avian excreta, as it's more formally known. At first, you're convinced that the bird must have deliberately targeted your car. But they're only stupid birds. They couldn't really do that, could they? Well, Charles West and Liam Chowdhury from the University of Bristol believe that birds may indeed single out particular cars for special attention. It's a radical idea, and like many great theories, it was conceived in a pub.
We were just a few of the mates, you know, having a little discussion, and one of them said, "Oh, yeah, I think that the birds, they poo on dark cars, or because they're similar colour to the sea, so dark blue or blue cars."
So immediately the debate started, and we thought if we get enough information, we'd be able to disprove this idea.
Buoyed by this desire, they enlisted 40 university colleagues and in just one day surveyed over 1,700 cars for bird poo. They created a simple table and filled in the number of poos next to the colour of each car. The final result was as surprising as it was conclusive.
We put all the information in, and out came the result.
Yeah, it was worthwhile us doing that, because it wasn't blue cars in the end. It turns out that white cars are the most popular ones.
Astonishingly, the birds in Bristol appeared to have an overwhelming preference for white cars, way and above all the other colours. So had they stumbled across something significant, or were their results a load of... To find out for sure, we need to know if little beady eyes can distinguish a car's colour as well as we can. Here's avian behaviour expert Professor Innes Cuthill from the University of Bristol.
Well, we're certainly proud of our own colour vision, and we can see much better than most other mammals. However, I think a bird would think of us as having pretty poor colour vision. Birds can see hues and wavelengths of light to which we're completely blind.
Human eyes are limited compared to birds because they're only sensitive to 3 colours of light: red, green and blue. On the back wall of the eye, tiny cells called cones fire off electrical signals when they're hit by the colour of light that they're sensitive to. In combination, these 3 cell types enable us to see a whole range of colours. Birds' eyes are sensitive to a 4th colour, ultraviolet. This means that their visible range is wider, and they're able to see colours that are impossible for us to even imagine. So birds have fantastic colour vision, but that doesn't really explain why they choose to poo on white cars. Professor Cuthill, for one, thinks that there must be an alternative explanation.
I guess my hunch was that rather than birds being selective as to which coloured cars they pooed on, it was something to do with where people with different coloured cars parked. So if they were more likely to park under a tree where starlings were roosting, or near buildings where seagulls were living.
To see if Professor Cuthill's parking theory holds water, Experimental set up an experiment. We swapped the motors for dustbins, one white and one black, and left them in an aviary full of seabirds from around the world. The question was which bin would prove more attractive to their bottoms. 1 week later, and the results were in. Would our experiment support the Bristol study, or would the doubting professor be proved correct?
And the results? The black bin has 3 poos, whilst the white bin has 7.
I'm frankly quite stunned. So that does suggest there might be something in this.
So assuming birds really do target white cars, the question remains, why? Experimental believes that the seagulls see the white cars as giant rivals who need to be dumped on.
Some birds certainly do use feces as a defensive weapon. Again, mainly seabirds, in conjunction often with vomit, they'll use their feces ballistically.
So while it does seem that, statistically speaking, white cars get a bum deal, the reason is something that science still needs to get to the bottom of.
I think we have stumbled on something here, haven't we? People want to know. People want to know if their cars are being targeted, don't they? Everyone feels a victim of bird poo. I think it's something they want answered.
Yeah, I think Bristol University needs 2 professors of pooology now, don't they?
Still to come on Experimental, the medical benefits of intestinal worms and what every techno-head needs for the kitchen. It's spring in the test department, and what better time to tend to the delicate plants and flowers in the test department garden? But what good is a garden without a water feature? Well, maybe a nice sit down will help to think things through. And what could be more refreshing for the brain cells than a cool glass of cola and a couple of chewy mints? Well, perhaps that's not such a great combo, but it does give our demonstrator a corker of an idea. You see, used separately, the cola and mints are a refreshing pick-me-up, but mix them together and things get a lot more interesting. Two things are probably happening. First, the mints reduce the surface tension of the cola. As a result, the bubbles of CO2 find it easier to break through. But that's not all. The CO2 bubbles also use the rough surface of the dissolving mint as a kind of ladder to help them make their escape. So there you go, an instant water feature that you can take anywhere, and it's good to eat too, although I'm not sure what it does to the plants. In our next visit to the test department, we'll be making the world's strongest house of cards. But first we ask how intestinal worms could help England win the World Cup in 2014. Asthma. At the very least, it can wreck a young footballer's dream of scoring 6 against Brazil. But for an estimated 180,000 people a year, it can mean death. But if Professors John Britton and David Pritchard from the University of Nottingham are right, there could be a cure, although not one to everybody's liking. That's right. A gut full of worms could be the cure, not just for asthma, but a wide range of other allergies too. Luckily, they are not the big variety, but parasitic hookworms, which grow to about 1 centimetre long. But why did the team think a worm might be the cure the world's been waiting for?
I think to understand why we're using worms to treat asthma, we have to go back to the immune system in its totality. If I can explain the immune system as simply as I can, it's a compartmentalized system. So you have one compartment that's geared up to fight bacteria and viruses, and another distinct compartment that's geared up to fight worm infections. And if that compartment overreacts, we develop allergic disease, rhinitis, asthma, hay fever.
One of the things that got the team interested in these little worms was when John Britton went to Ethiopia to study asthma.
There's good evidence that around the world, when countries become more affluent, the prevalence of asthma and some other traditional Western diseases increases. We looked at the prevalence of asthma in the urban area of Jimma in Ethiopia and then in rural surrounding villages. And we found there was a great deal more asthma in the town, not as much as you would get in a developed country, but a lot more in the town than in the surrounding areas, just a few miles away.
When he discussed this with Prof. Pritchard, who had been looking at the effect of hookworms on populations in New Guinea, the pair became convinced that hookworms might be having an effect on the immune system. The idea isn't new, it's been around for decades. Their theory is this: the part of the body's immune system that has evolved to fight worm infections is also capable of going on the rampage and causing problems like asthma and hay fever. The good news about hookworms is that they seem to have discovered a way of pacifying the immune system. This allows the worms to live in peace, but might also stop the immune system from causing allergies. But how did they test the effect the worms were having on the immune system? You've guessed it. Luckily, you don't have to eat the worms. Worse, they eat into you. They're microscopic larvae chewing through your skin. Nice. In a blind study, the team infected 10 healthy adults with between 10 and 100 worms. But what was the perfect dose? Too few and nothing might happen, and too many and you could end up feeling very ill indeed.
The person who got 100 is the bravest person, and she felt pretty sick.
In fact, as it turns out, 10 is more than enough.
So far, the team's results suggest that a small infestation of hookworms does have an effect on the immune system. But will it stop allergies like hay fever and asthma?
Here's the infection that we're going to give you.
The first trials are starting up, but will people want their guts full of worms, even if it stops them wheezing?
This could be a major breakthrough. But ultimately, the pharmaceutical industry will want a hookworm mimic, a molecule from the parasite that mimics the effect of the whole infection. So that's the downstream ambition of the project.
Pill or worm, it will come as a welcome relief to anyone whose life is plagued by a tight chest and the dreaded wheeze. Before Experimental heads to the kitchen of the Massachusetts Institute of Technology, let's head to our own institution for a spot of R&R. There's a card school going on down at the test department. But being the test department, it's no poker game. The money is on whether it is possible to build a house of cards strong enough to take someone's weight. Here are two ways of building a card house, both borrowed from real engineering. The traditional truss form with its ziggy-zaggy bits and the more modern closed cell system. In the real world, the truss system was much loved by Victorian engineers who could knock out super strong bridges in a couple of weeks. The forces being directed down the diagonal beams. The cell system is often used in skyscrapers where a strong core of cells is built in the middle, which supports the weight of the floors and exterior walls. Going for aesthetics, the test department first tried the truss, but didn't get very far. Next up, the closed cell system was tried. It's a lot easier to build and soon half the table is covered with cards. But can this structure take the weight of a test department demonstrator? Let's see. Fantastic. Rock solid so long as the forces are straight up and down. Subject it to a simulated earthquake with the forces coming from the side, and it collapses. Well, like a house of cards. Finally on Experimental, cooking for nerds. In Cambridge, near Boston, Massachusetts, is the home of Leonardo Bonanni, a man who wants to revolutionise life in the kitchen. Currently, he's developing his ideas in the Media Lab at MIT and is part of a group they call the Counterintelligence Group.
We're in the kitchen of the Media Lab. Kitchens have always been a very technological space and the first place where most technologies enter the home.
It's a pretty cool place, full of things like indoor greenhouses to keep your salads alive for a month, cloths that tell you the heat of the food as you bring it out of the oven.
Careful, it's hot.
And this prototype tap, which tells you if the water is hot or cold. But pride of place is this, thing. Leonardo's dishmaker. What gets Leonardo's goat more than anything else is crockery. It's not the washing up he doesn't like, it's the space the stuff takes up. So his idea is a machine that makes the tableware right there in your own kitchen.
The dishmaker that you see here is still an early prototype. We've only been working on the concept for 2 years.
2 years? Blimey. They're not exactly big on finish at the Media Lab, but the concept is cool. The idea is this. Dishes take up a lot of space. But if we can make them flat, they take up next to no space at all. So the idea of the machine is that you have a small box in the kitchen filled with hundreds of flat dishes that can then pop out finished crockery like this at the touch of a button. Brilliant. It seems Leonardo has managed to add a big machine to your house, which can produce hundreds of plastic plates that you then have to store. A bit stupid, that. But actually, it's not that dumb. Once you've used the dish, you put it back in the machine, press another button, and it goes flat again.
It will always remember how it used to be, and it will be able to pop back, like a rubber band. When you stretch rubber, it always goes back to the same shape. Here, you have to soften the material with heat to stretch it out. Once you cool it, there's a stress in it, and so when you heat it again, like a rubber band, it pops back to the shape that it used to be.
This phenomenon is called shape memory, found in some plastics. Take Captain Plastic here. So long as he doesn't get too hot, he's as strong as they come. But whack a bit of heat on him, and you can push him into any shape you like. Take the heat away, and he'll stay down, even though he's constantly trying to get back into his original position. To get him back there, all you need to do is to reapply the heat, and he'll do the rest. Ultimately, Leonardo hopes that machines as small as this could supply large institutions with all their crockery needs, freeing up masses of storage space.
I think this prototype shows the basic concept, which is to make dishes and recycle them all within a machine the size of a dishwasher that doesn't consume any more power than your toaster oven.
All very clever, but Leonardo hasn't managed to crack the biggest problem with crockery in the kitchen. Sure, the machine can recycle just fine, but it can't do the washing up.
The rally car is fast, but speed isn't everything. This machine is built for trouble, from the ground up. And when you see a cuckoo this big, on a mechanical clock this tall, you gotta wonder what makes it, well, tick. The lift lock is a giant elevator that raises boats in a 2 million liter tub, all without gas or a motor. The web offset printer, high-speed printing at 20 kilometers per hour without a single smudge. Let's take a look inside these machines and see how they work. This is a rally car. It may not look like much sitting here, just a regular car with a few bells and whistles under the hood, right? Wrong. This machine may look like a Clark Kent, but once it's turned on, it's a supercar. The ride you pick up at the local dealer is related to the rally car, but we're talking distant cousins here. Really distant. In fact, the only thing that's left from your car on this machine are the lights. Turbocharger, big brakes, steering. It's all redesigned for speed, control, and handling. To beat an insanely difficult course without killing anybody. Let's see how it works. First, speed and control. Two things make that happen. The engine for acceleration, the brakes for taking corners and maintaining control. High-end rally car engines pump out over 300 horsepower. Thanks in large part to its turbocharger, which is basically a turbine placed in the car's exhaust. The turbine spins up to 150,000 RPM, 30 times faster than the engine. All that spinning powers a compressor that sucks in the air from outside, compresses it, and injects it into the engine's combustion chamber. More air means you can burn more fuel, with explosive results. And all that power shows up here at the start line, where it rockets the car up to 100 kilometers an hour in under 4 seconds. And that speed is great on the straightaways of a rally course. But these races are won and lost in the corners, where small mistakes cost valuable time. To master corners, this machine needs some serious stopping power. And it comes from some of the best brakes money can buy. Most cars have disc brakes with a single piston that move a brake pad onto a disc that slows the wheel. But they would literally disintegrate out here. A rally car needs as many as 8 to maintain speed and control. What about this challenge? A 180-degree hairpin turn. Top drivers make it look easy. A regular car and its driver? Not so much. Rally cars come equipped with a powerful handbrake that allows for this kind of action. You may use yours to park, but this machine's not built for standing still. Its lever sits next to the steering wheel, so the driver can grab it quickly. An independent hydraulic system locks the car's rear wheels, and around you go. Now that's what this machine is all about. It's also about staying in one piece. In a rally car, every seam gets a continuous weld, including the roll cage. This molds the body into a single unit, so on impact, the shock is evenly distributed. On top of that, the roll cage is structured with triangles directly to the frame. The cage is made of chromoly, an alloy that is lighter than steel and stronger too. The triangle design distributes force evenly, allowing it to withstand crushing blows from all directions. So not only does the rally car survive a rollover that would crush your average car, it recovers and keeps on going. The roll cage also provides a rock-solid base for the shock absorbers. Each has 2 key components: springs and dampers. They work together to absorb everything the road dishes out. The problem with springs is that they tend to expand as quickly as they contract, which makes for a very bouncy ride. The damper, a hydraulic chamber with a piston inside, controls the expansion and vibration of the springs, maintaining critical contact between the rubber and the road. Low and stiff for road races, high and loose for off-road. A set of 4 sets you back about 7,000 euros. But if you cheap out on the shocks, you'll pay a price out here. It's also all about staying on the road. The steering wheel is coated with a felt that locks in the driver's gloves like Velcro. You don't want to lose your grip out here. So rally cars are designed to keep control panels as close as possible to the driver. These paddles shift a gear in 50 milliseconds without the driver ever letting go of the wheel. And that's important because the difference between winning and losing a rally race is measured in fractions of seconds. When driver and machine get it done right, the champagne flows. If either slips up, the results are decidedly more painful. For speed, agility, and durability, nothing compares to a rally car. This machine may look like the one in the showroom, but don't go bringing your ride out here. This domain is reserved for the supercar. Welcome to Marienplatz Square in Munich, Germany. Home to a tower which houses one of the world's great mechanical timekeepers and a little number called the Glockenspiel. Its parts are spread out over 8 of this tower's 11 floors. Parts that include a bunch of these guys, a giant music box, a room full of gears, and 7 tons of bells. 100 years of gonging, cavorting, ticking, and talking. Let's see how it works. And let's start at the center of this machine with its amazing clock, which, like all big mechanical timepieces, is driven by a pendulum. Pendulums give us tick and tock, as well as the means to measure time accurately. But to do that, clockmakers have to overcome several stubborn challenges. The first is getting all of its parts to move at a precise unit of time that is repeatable, like 1 minute. So how do you get a minute hand to move precisely every 60 seconds? It starts with a little help from gravity, which gives the pendulum its perfect timing. You have to adjust its length until the swing lasts 1 second in each direction. That's it. The pendulum's weight doesn't matter. Gravity is constant. Neither does the distance it swings. All that matters is the length. And in order to work accurately, every pendulum is bolted to this, the escapement. As the pendulum swings past its center point, the escapement's teeth allow the gears to escape, one at a time. This creates a familiar sound we all know as tick. And as it swings back the other way, you guessed it, tock. Which leads us to a second challenge, how to beat friction that wants to stop the pendulum. After every tick and tock, the special shape of the teeth give the pendulum a very slight snap, which travels down its shaft. It's not much, but it's just enough for the pendulum to overcome friction and keep moving to the end of its swing. Oh, and if you're wondering about this small clock face here, it allows technicians to keep track of the time on the tower's giant clock. Imagine having to run down the tower and into the square to check it every day. Okay, so the seconds are ticking by perfectly. But how does that turn into this? A series of metal rods connect the mechanism to the clock. The muscle to move the giant hand comes from a hanging weight. Same idea as the one on your grandfather clock. When the weight falls, this cable turns gears, which turn the rods, which turn the hands. And that sets up the machine's third challenge. How does the escapement keep the whole thing from spinning out of control? It counts out the seconds, and after 60, lifts a release arm that's been stopping the weight from falling. The weight is released for a fraction of a second, just long enough to turn the gears that turn the hands. This repeats every minute. As the weight nears the end of its run, a small motor winds it back up to the top to start dropping all over again to power the clock. But there's one more challenge. In making timepieces this big, clockmakers created a problem. Bad weather pushes on its hands, which transfers back through the gear train. The heavy weight can resist the force, but can damage the escapement mechanism. So they installed a mainspring called a remontoire that drives the escapement, which powers the pendulum. When the weight falls, it rewinds the spring. This gives the escapement the power it needs while isolating it from brutal forces outside. So there you have it. This is what makes a giant tower clock tick and talk. All right, now let's check out the glockenspiel. On level 9, a supersized version of your grandma's music box. It transforms individual notes from a song into electrical signals with these metal pins. Those signals control the gears on this table that yank long cables that in turn pull on clappers, clanging out classical tunes on 7 tons of bells. Each pin sends a note to each gear that plays a bell, and each bell plays its part. For these life-size figures on the 8th floor, which are driven by an electric motor and a set of gears. Jousting knights in one show, dancing barrel makers in another. And then a rooster pops out for good measure. It's a bit like an old cuckoo clock, only with more gears and bigger cuckoos. Floor show or not, it's the pendulum that counts on this machine. And you'll find it on every mechanical clock there is, cuckoo or not. This is the Peterborough lift lock, located an hour and a half north of Toronto, Canada. It's a pivotal linchpin of the Trent-Severn Canal, a 386-kilometer waterway that allows boaters to travel with ease between the Great Lakes. Built in 1904, it easily hauls 1,500 tons of water, equivalent to almost 1,300 passenger cars, from bottom to top in under 90 seconds. All without using a single watt of electricity. Okay, the control panel lamps are electric, but that's it. It's also the highest hydraulic lift lock in the world. Let's see how it works. Lift locks are built when a canal needs to get past a natural barrier, like a waterfall. That's where the lift part comes in. So, how do you do all that without motors or electricity? With help from gravity and water. This guy fires a piston beneath the lock to raise this gate on the bottom tub. This separates you from the canal. And that leads us to our first problem, lifting a giant tub. All it takes is water and gravity. The lift lock is like a seesaw. One side goes up, the other has to go down. But the top tub needs more weight to do that. An extra 30 centimeters of water flows in here. That makes it 144 tons heavier than the bottom tub. It uses water for weight because as far as this machine is concerned, you and your boat are weightless. As your boat floats, its total weight displaces its equal weight in water. So no matter how many boats are squeezed in, the weight never changes. Okay, so we're moving thanks to that extra sip of water in the top tub. But how exactly are we moving? What's preventing this 2 million liter bathtub from smashing straight down into the canal? 2 identical rams riding on a cushion of water. The rams move inside these cylinders called press wells. As the top tub descends, it drives the ram beneath it down. Water in the press well is then forced up this narrow space and channeled through a connecting pipe to the other side of the lift lock, where it forces the second ram and the tub on top of it up. When the ride is over, the guy upstairs shuts off a valve located in the center of the pipe that joins the two press wells. This locks the tubs in place, and you're free to fire up your boat and motor away. It may be old, but the engineers that built the Peterborough lift lock knew a thing or two about green technology. Water and gravity. Simple. A century on, still the highest hydraulic lift on record. Major daily newspapers in London, New York, or Paris have only a few hours to print over 1 million copies and get them on the street. And they couldn't do it without the web offset printer, a machine that prints non-stop from feeding to folding without a smudge. It's called a web offset because of the configuration of paper paths. For newspapers, it's the fastest and cheapest form of high-volume commercial printing. 11 kilometers of paper in just 40 minutes, changing the rolls on the fly without stopping. The paper runs through this printing stack at up to 10 pages per second. And these rollers are the key to the machine's ability to spit out such high-speed precision. Here's how it works. The actual printing plate is a flexible aluminum sheet that wraps around a drum. But on a closer look, that's a smooth surface. How does a printing plate make an impression with no raised edges? It's based on the fact that oil and water don't mix. A special coating on the aluminum plate is designed to absorb oil-based ink. So, if we ink this plate now as it is, it would produce solid black. So, ultraviolet light is used to project a 4-page digital image onto the plate's coating. The parts exposed to the UV light harden in place, while the unexposed parts of the coating dissolve away in a chemical bath. Emulsion and bare metal now form a printing plate. Once loaded on the print cylinder, the plate collects ink and water from rollers. The hardened sections of coating absorb ink. The other parts of the plate take on a film of water that keeps the non-printing areas ink-free. So, the ink-coated plate is ready to transfer, but not directly to paper. That would wear out the plate too quickly. The metal plate is wrapped around this drum. The ink image is offset from the plate to a rubber roller called a blanket, and the rubber then transfers it to paper. That's why it's called offset printing. Now, to print both sides, the paper is sandwiched between an opposing set of plates and rollers. With a 4-page printing plate on each side, one turn of the drum produces 8 pages in 1/10 of a second. It's all black and white. But what about photographs? How does this machine print gray? Well, it can't. But here's how it works. A photo is filtered through a screen, and the gray tones are broken down into black dots called halftone. The closer together the dots, the darker the effect. Pull back, and the halftone image appears as gray. We make up color the same way. When you mix black and 3 primary colors, cyan, magenta, and yellow, you can create every color that exists. The original color image is split into 4 halftone plates. 3 plates carry one of our colors, and the 4th carries black. The color inks are loaded into the machine. Then, the plates are printed one after the other with halftone dots. And as long as they are perfectly lined up, our perception once again connects the dots into a continuous tone. This press has 6 printing stacks. The tall stacks have 4 sets of drums so they can print in full color, and the smaller ones just print black. The web of paper feeds through the stacks from both ends and meet at the collator. The machine collates, folds, and chops the newspaper, then sends it along to be stacked and bundled at over 500 copies a minute. The web offset printer set the standard for hot off the presses. Even in today's digital age, nothing can beat this machine for volume, speed, and cost.